pleasure to introduce my friend and collaborator, Jeff Byers from Boston College. Jeff's an associate professor at BC now. For his path there began growing up as a youngster in New Mexico before obtaining a BA at Washington University in St. Louis. I got to know Jeff when he was doing his PhD studies at Caltech in the Burkha lab. So we overlapped as graduate students for a few years. And I was very lucky to be coming up after him because he taught me all sorts of things about especially chemical kinetics and understanding mechanism and understanding how to break opponents down on the basketball court. And hit step back jumpers. So Jeff is talented in many ways, and we got to be good friends there. So after obtaining his PhD in California, he flew across the country and did a postdoc at MIT with Jameson before starting at Boston College. So he's been recognized with many awards, including an NSF Career Award and a Cottrell Scholarship. And I think those balance of incredible scholarship and teaching ability, as well as innovative research, are highlights of Jeff's style. So I won't take any more of his time. I'll turn it over to Jeff. Floor is yours.
All right. Well, thank you, Alex, for the nice introduction. And it's my pleasure to talk to you guys today about controlling sequence and polymerization reactions. What is sequence in molecular science, and why is it important? So we'll start off with the first thing. So you can think about sequence in polymer chemistry in a lot of different ways. And so I've kind of highlighted some canonical different kinds of ways that people think about sequence. So you can make a polymer that is consisting of different monomers, and those monomers can be organized in different ways in a polymer. So for example, if you have a polymerization between two different monomers, you can envision a copolymerization that gives a block copolymer sequence. Let's see if I can change my pointer. Yeah, a block copolymer sequence, an alternating copolymer sequence where we alternate A, B, or a site-specific copolymer sequence where you have kind of mostly A and then occasionally you get a B. And so those are all possibilities. If you have more than two monomers, of course, things become a lot more complicated, complex. And so if, say, for example, you have three different monomers that you're polymerizing, or three different possibilities, you can come up with a periodic polymer like this one, where you have an ABC sequence, ABC, etc. And then, of course, if you have a lot of different options for your monomers, then you can have A, B, C, D, E, F, etc. And so these sequences, in principle, have a lot of different possibilities. So this brings me to my first poll question. What is the maximum number of different sequences that can be obtained from a polymer derived from the same monomer? I can't see the answers, Julio, so you're going to have to help me. How are we doing? Everyone answer by now?
Yeah, there we go.
Okay.
You should be able to see.
Can you show the results? I can't see the results. All right. So about a third of people say only one, a third of people say an infinite number of possibilities, and a third of people say not enough information. And so the right answer is not enough information. I don't know what's going on here. Because it depends on the identity of that monomer. So those of you who answered not enough information, you guys are correct. If you have an achiral monomer, then you can only make one sequence, right? So if you have one monomer, that's all you can do. So those of you who answered one, you're assuming that the monomer is achiral. But you can have prochiral monomers like this propylene monomer, which is the same monomer. And depending on the catalyst that you can use, you can actually synthesize different polymers that have different stereoregularity in the polymer. And this is a type of sequence control. If you think about each monomer being derived from a different stereoisomer. And so here you can have a catalyst that maybe gives you random incorporation of propylene with the methyl group coming out of the board versus going into the board, which is called isotactic polymer. You can have a catalyst that maybe controls polymerization of propylene to give you just everything coming out of the board, which is isotactic polymer. You could have one that's random, alternating back and forth, which is called syndiotactic polymer. And then there's also the possibility that you can have large blocks of one and then it changes to the other. And so that's called a stereo block copolymer. And so many people don't consider stereochemistry as being important in sequence control, but it totally is, because as you know, if you were to make these molecules and you had two chiral enantiomers, those two are different molecules, even though they are mirror images of one another. And it turns out all these polymers have different properties, and so that's an important thing. So good job for those of you who said not enough information. Very savvy of a third of you guys. So why do we care about sequence? So firstly, thermal properties can be affected. So here is a copolymer between butadiene and this acrylate polymer that has a chlorine in it in the alpha position. It's been hydrogenated. And it's compared to a random copolymer of the same of polyethylene and the acrylate monomer in a roughly 2-to-1 mixture. And over here, you can see here is a Dsc trace, which I'll talk about in a second, what a Dsc is, and also a powder X-ray diffraction. And so before we can look at this Dsc trace, I think it's important to understand what Dsc is. So for those of you who are not polymer chemists, hopefully will be instructive. For those of you who are, just bear with me. Dsc is differential scanning calorimetry, and basically it's a calorimetric method wherein you have these two pans, as you can see down here, these little tiny pans, one in which you put a reference, which is just basically the pan, and the other is the pan that contains the sample in it. And then you heat both pans up, and what you measure is the difference in the heat capacity between the reference and the sample pan. And if there's any phase transitions, what happens is there will be a difference in heat capacity in the heat absorption for the sample pan versus the reference pan. And so then you can get heat flow into the pan or out of the pan depending on what kind of transition there are. And so here's a typical Dsc trace that you might see if you did a Dsc of a polymer. So if you increase the heat flow into the pan, then you have a recrystallization. So that would be something that would go from a liquid to a solid. You can have that when you're heating it, when you're cooling down something, but also you can see it sometimes when you're heating up a sample. So that's kind of odd that you might see a recrystallization, but that's actually not so uncommon in polymer chemistry. Here, as you might expect, you can see melting temperatures. So that's usually indicated with a dip in the Dsc trace. And then this little kind of inflection point here is something that's special to polymers, which is called the glass transition temperature. And so this is the temperature in which something goes from an amorphous state to from a glassy state to a non-glassy state. And essentially what it is a measure of the mobility of the side chains in a polymer sample. So if we go back to our polymer, you'll see that the alternating copolymer here has very different thermal properties than the random copolymer. Namely, we have a very high TG, so it's a TG of a 76 compared to 37 for the random copolymer. And also there's a melting point for the alternating copolymer that doesn't exist with the random copolymer. And as a result, you can see in the X-ray, powder X-ray diffraction that the crystalline polymer is the one that's from the alternating copolymer, whereas an amorphous polymer is produced from the random copolymer. So this sequence, having this ordered sequence of random versus alternating copolymers can affect the thermal properties and can dictate whether the polymer is an amorphous polymer, which is often stretchy, and a crystalline polymer, which are often more rigid. And so Nate, here's another example where we can look at mechanical properties of a sequenced polymer. So here is a polyester where we have a random copolymer of these two monomers. And we can compare it here to the blue monomer, which is an AB alternating copolymer of those two polyesters. So this is a random sequence, and this is alternating of these two polyesters. And on the right is a tensile test for this polymer. And so I wanted to explain briefly what a tensile test is, because I think for most chemists, they're not used to seeing these kinds of stress strain curves, but they're important when you're thinking about polymer properties. And so this is the experiment. Basically, you cut a sample of your polymer or any kind of material that you want to measure into this dog bone shape. And this is dictated by engineering standards. And then you put it into this cantilever here that holds the sample. And then you pull apart the sample until it breaks, essentially. And there's different ways to run this measurement, but oftentimes it's either done with a constant strain, so a constant amount of force that's being applied to the sample, a stress, excuse me, a constant force applied to the sample, or a constant strain. So that means that a constant rate of it going, of the two cantilevers kind of pulling the sample apart. And as a result, what you get if you apply the stress, which is the amount of force that you're applying to the sample, to the strain, which is the amount of deformation that you're giving to the sample, you often get curves like this, where you have an elastic region. So if you take the sample and you deform it to point B and then you let it go, it's going to return to its original state. But if you continue to stretch the sample and you get to this point here, to point C, then you start to enter this so-called plastic region. And so many people use the word polymer and plastics interchangeably, but that is not how we should be using those terms. Plastic is a kind of behavior of a material, and many times polymeric materials have plastic behavior, and so they're often used interchangeably. But here, if you can see, if you stretch the sample to point C, now you've started to go past what's called the yield point. And so now when you release that sample, it no longer returns to the original length of the sample, but instead it goes to a different length. And so you can see this. I'm sure you've experienced this with like silly putty. If you take silly putty and you stretch it a little bit and you let go of it, it will collapse. But if you stretch it too much and you let go of it, it'll just kind of retain its shape. It might go down a little bit. And so that's exactly what you're seeing here with this stress strain curve. And eventually, if you keep on putting stress onto the material, then it fractures and it breaks. And so that's the end of the stress strain curve. Okay. So just a couple of more engineering properties that are important. Here is E. This is the Young's modulus, which is the stress divided by the strain. So it's basically the slope of this initial curve when you're in the elastic region. The yield strength would be when it starts to bend over, right? And so it's no longer elastic deformation. It's inelastic deformation. The ultimate strength, this dotted line is a little bit low. It's right here at the stress at which the material breaks. And then the toughness of the material, which is the area underneath that curve. So things that are very tough can undergo lots of deformation and also can take a lot of stress, excuse me. So they can hold a lot of weight. And so something that is not very tough may be something that you can put a lot of stress onto it, but you can't deform it very much. So things that are tough, you can deform them and also put a lot of stress onto them. And then finally, the elongation at the break, this dotted line is also a little bit off. It should be right here. This is how far you stretch the material before it breaks. So that's the basics for these stress strain curves. So let's see what you know now in that crash course. Which of these polymers, A, B, C, oh shoot, I don't have D. There's no C, sorry guys. A, B, D, or E, which of these is the elastic polymer? All right. Okay, so we have a variety of answers. 41% say A is the elastic polymer, of the elastomer. B, some people say it's B, and the smallest number of people say it's D. Of course, I'm glad no one answered C because there's no C. So let's show you what all these different kinds of polymers are. Let's see, getting out of the. Here we go. This is a brittle plastic, so this is not really an elastomer. You can't really stretch it very much before it breaks. So this is not a very good plastic. No one would call that an elastomer. This is a hard and tough plastic, so you can see that there's a large kind of area underneath the curve here, and so that would make it very tough. It also has a relatively large modulus, and so that's a pretty good material that would probably be classified as a thermoplastic elastomer. This is a tough and strong plastic, so it's a little bit stronger than the hard and tough plastic. But our elastomer is actually E. So this material you can stretch really far before it breaks. And it has a pretty decent elastic regime here. You can see it yields a little bit, but it still will return, pretty much to the original length. And so this is the kind of curve you would expect for something like a rubber band. This is the kind of curve you might expect for something like polystyrene, which is not very stretchy. So styrofoam, as you know, you can't really deform it very much. All right, so let's go back to our polymers that we were looking at and comparing with sequences, random copolymer versus an alternating copolymer. You can see here with the random copolymer that we have a much more flexible material. So this is a much more tough material, the random copolymer, compared to the alternating copolymer. Here you can see that they're pretty much the same strength, right? The modulus is almost identical for the two polymers, but you cannot deform the alternating copolymer before it breaks as much as you can with the random copolymer. And so this is, it's not necessarily true that you always want to have a perfectly, sequenced polymer. Depends on the application that you want. But what you can see here is by changing the sequence from an alternating copolymer to a random copolymer, we change something that would be a stiff plastic to something that would be more like a thermoplastic elastomer. And so this is a good example of how sequence can control mechanical properties. Okay, what about degradation profiles? So we've been talking a lot about plastics, and they're in the ocean, and how do we deal with these? And this is a big problem. And so there's a big interest in biodegradable polymers, and a leading candidate in biodegradable polymers are polylactic acids, as well as polylactic acids that are copolymers with glycolic acids. And so actually these PLGA polymers are quite common in dentistry. So if any of you guys have ever had your sutures in your mouth from wisdom teeth, you've had polylactic acid in your mouth and polylactic glycolic acids. And so here, Tara Meyer at the University of Pittsburgh has developed this really nice synthesis to synthesize alternating copolymers of polylactic acid and polyglycolic acid, which doesn't have the methyl group. And she's comparing it here to a random copolymer of the two, now with a stereo center here in this sample, and here where it's stereo random. So this is my final poll today, so I won't quiz you too much more. But I'm curious, which of these do you guys think degrades the fastest? The low molecular weight alternating copolymer, which is the 16 kilodalton material. The higher molecular weight alternating copolymer, 26 kilodaltons, or the one of the two random copolymers. All right. Okay, most people think that the polymer that's going to degrade the fastest is the low molecular weight alternating copolymer. So let's see what the answer is. Close that. Hopefully I can. All right, so here is a plot of the molecular weight at time t divided by the molecular weight at time 0 of these polymers when exposed to pH 7 buffer. And as you can see here, the dotted line is the one that everyone guessed would degrade the fastest, and that's the exact opposite of what is the trend. Here, the one that degrades the fastest is this blue line, as you can see here. The blue line is the polymer that is derived from the random copolymer of poly-L-lactic acid and polyglycolic acid. That one degrades the fastest. And then the slightly slower is the green here, which is the R-SAP, which is involving the L-lactic acid and the glycolic acid. And then the slowest actually are the two polymers that have the alternating sequence. And as you can see, there's a molecular weight dependence on these polymerization reactions. And so this is really important because it turns out that this polymer here that degrades the fastest has the worst physical properties, the worst mechanical properties. It's the most amorphous. And so oftentimes that's the case when you have a crystalline polymer that can organize itself. So these with either the stereoregular polymer or an alternating polymer, as in this case, you see stiffer polymers that then have a harder time to degrade because the crystalline polymers have a harder time for the water to get to the esters to hydrolyze. And so these kinds of polymers, as I mentioned, are useful in biodegradable sutures, but we're also interested in using these as engineering polymers and also as drug delivery devices. And so all of us are getting the vaccine very soon, and a very important component of the vaccine is the drug delivery device, which is something that allows the mRNA vaccine to get into the bloodstream. And we don't know what those are made of, but I work a little bit with Moderna, and so I know some stuff going on there. And these kinds of polymers are certainly things that they have discussed with me in the past. So it's these kinds of lipid nanoparticles, which can be derived from polylactic acid, can be very important for a variety of applications. All right, and so this also came from Tara Meyer, who's done some really great work in this area. And she explains this difference in reactivity, as I mentioned, with the fact that there are different sites for hydrolysis, those from lactic acid and those with glycolic acid for the random copolymer, whereas the sequence control polymer only has one site, two sites for hydrolysis. And it turns out the more amorphous sites that have the glycolic acid is where the hydrolysis occurs first. And so if you have a lot of A sites in the random copolymer, whereas you have none in the alternating copolymer, you get faster hydrolysis. Okay, now I wanted to talk a little bit about how sequence is controlled. And so, of course, the master of sequence control is biology. And so everyone, I hope, is familiar with DNA and nucleic acid sequences. And so our genetic code is derived from these nucleic acids, and without it, we wouldn't have life and genes and all this kind of stuff. And so the code that is dictated by the base pairs that are from these double helices, of course, are macromolecules. These polyphosphate nucleic acids that form the double helices that is famous in DNA. But in addition to that, nature also has sequences for the amino acids, and so polypeptides and proteins that are derived from all the natural amino acids also have excellent sequence control, and that also dictates their properties. And so here, primary structure of alanine, valine, all these different amino acids, they can, in the right sequence, can either form alpha helices or beta sheets, depending on what the side chains are and the sequence of those side chains. And that leads then to tertiary structure that then allows the proteins to fold, which can also lead to quaternary structure where more than one proteins can fold. And so you guys probably have heard this story before, but I think maybe one thing you haven't heard about is how this is appropriate and necessary and useful for engineering polymers. So things that have physical properties that we may want. And one of the most amazing materials on the planet is spider silk. So this material is derived from polypeptides, and it's some of the strongest materials that we have, and also some of the toughest material that we have. So for example, on this list, here's Kevlar, right? Bulletproof vest. It's very strong, but it's not particularly flexible, right? Also, where's carbon fiber also is pretty strong and not very flexible. But here, depending on the identity of the silk, of the dragline silk from spider silk, we can have something that's very strong and also very tough and not so stiff. And also, it turns out I don't have density on here, not very dense either. So it's kind of amazing material, spider silk. And if you look at spider silk, and people have studied this, and if you're interested in spider silk, I look at this Advanced Physical Applied Physics B article here, and the drag line is what has the most the best engineering properties. And if you look carefully at that drag line, it has these peptide sequences that have the alternating glycine alanine alternating, and then there is a crystalline domain that's from a lot of alanines that are together. And so you have this alternating sequences of these amorphous domains and crystalline domains that then can stack together. And this is what comprises this blend of materials is what comprises the spider silk. And so we're still trying to mimic this. So we're not really good at this. Synthetic chemists can't mimic spider silk very well, but it's certainly something that we can take inspiration from. Here's another, I forgot I had the this slide in here, but here's a nice another sequence, and this is a great review as well of spider silk material. Okay, so I wanted to finish today by talking about the methods that we've used to synthesize polymers with synthetic polymers with sequence control. And the first part of this section will focus on precise sequence control. Please come back later. And the second will involve imprecise sequence control. Peptide synthesis, as I mentioned, is at the heart of this. And so there are actually 2 different Nobel Prizes awarded to peptide synthesis. That's how important it is. And there might be a third one on the way, who knows? And this is the first example of a peptide sequence. And so sorry to my physical chemistry colleagues, I've tried to highlight the residues here, and the bond that we're making is the peptide bond here in red and blue. And this is an example from de Vigneault, and this is an awesome paper. I would totally recommend reading this. So for those of you who think that no good chemistry was done before the 2000s, check out this 1954 paper, and you will be humbled, because no NMR spectroscopy, and they were able to make these amazing molecules, and they figured this all out using classic techniques. But what was really revolutionary here was the strategy for making peptide bonds. Here they used protecting groups to prevent the reactions from occurring at this N-terminus, as well as there's an O-terminus protecting group. And so you only get bond formation at these 2 positions. And also making amides is still a huge challenge in organic chemistry. And the state of the art at the time was using these coupling reagents to make that amide bond. So a stoichiometric coupling reagent, which is still actually the state of the art. So we need catalytic methods to make amides. And then deprotection sequence. So the sodium ammonia dissolving metal reduction then reveals the NH terminus, which you could then couple again if you want. But in this case, they were done with their peptide synthesis, and they were ready to make the cyclic peptide that they were actually trying to make by making the thiolate. But this strategy was then replicated in the solid state. So this was all in solution. So they have all this stuff in solution, and that can be really tedious and difficult to purify. And so Merrifield in 1984 won the 2nd Nobel Prize for making peptides. And what he demonstrated is that you can do this all in the solid state, a solid support. And so this is a polystyrene bead that you can then react with a Bach protected amino acid. So the protecting groups and coupling reagents have changed a little bit. So that's the Bach protection. The DCC coupling, that has also fallen out of favor these days. But this carbodiimide coupling is very classic. So many of you probably have learned this in sophomore organic chemistry to make your amide bond. and then TFA deprotection, followed by another round of coupling. And so you can go over and over and over again, this kind of coupling, deprotection, coupling, deprotection, and then you can make large polypeptides. And so in fact, there are instruments that do this, and this is a peptide synthesizer that you can see, and you can put your amino acids in these tubes, and then in these reaction flasks, it will make your polypeptides. And at the end of the day, when you're ready, when you have your peptide, you can then cleave it off the surface to make poly amino acids. The problem with this strategy is that it's very laborious. Fast peptide synthesizers can couple, deprotect in 4 minutes. So if you wanted to make a sequence that's 100 mer, that would take about 6.5 hours. And that's only about 13,000 molecular weight. So it's not a very large peptide in 6.5 hours. It's not a very fast reaction. It's very wasteful. So all of these steps are stoichiometric, right? We have to protect the amino acid. That's stoichiometric. We have to use these coupling reagents. That's stoichiometric. When we deprotect, then we blow off some of the molecule. And then also all of these steps involve a lot of washing of the polystyrene bead to get rid of excess reagent. And so it's very wasteful. And then it's not scalable. And so today I looked and to try to figure out what was the largest scale anyone's done these kind of solid state peptide synthesis on. And it's something like 50 kilogram scale is it. So this is not something that you're going to replace. You know, we're not going to make spider silk, for example, on a solid state peptide synthesizer because we're not going to ever make enough of it to make it a difference as an engineering material. So people have been thinking about other ways to make sequence control polymers. And here's one of my favorites. It's called Segmers, also from Tara Meyer's group. And what she's done here is to kind of mimic that protection, deprotection sequence to make dimers. So here you have a protected carboxylic alpha hydroxy acid. You can then do a similar kind of coupling reaction as what was done in the peptide synthesizer. You can then deprotect with TBAF to then reveal the hydroxy acid that has now a glycolic acid and a lactic acid unit. And then you can take this acid alcohol and subject that to stoichiometric DCC coupling. And if you use a stoichiometric amount of the reagent, you then get condensation polymerization. And this is how Tara made that alternating copolymer that I showed you the degradation results for. Okay, alternatively, you can do a different sequence of events. Actually, there should be palladium, a hydrogenolysis reaction here. I apologize for that typographical error. If you don't do both deprotections, you can actually just hydrogenate the benzyl ester to then leave the siloprotection group on the molecule, and that allows you to put another residue on with DCC coupling. So now you have a trimer that you can then deprotect, hydrogenate, and then polymerize. And so in so doing, you can then make that stereo complex where you have the RS glycolic acid periodic polymer or the SS glycolic acid periodic polymer. And so this kind of Segmers way, we can avoid some of the limitations of solid state peptide synthesis because in the polymerization reaction, we are not doing this kind of sequential protection, deprotection, protection, deprotection. We just do that once when we make the monomer. And then we deprotect, and then we do the polymerization. And so we can get to, Tara can get to high molecular weight materials that she can then study. And these have really cool NMR spectra. That's the other thing that's neat about these stereo or these sequence regular polymers. They don't look like polymers at all. They look like small molecules because the sequence is so perfect. And so that allows you to assign the resonances for random polymers. And so this is a really good use of these kinds of Segmers, is to try to figure out what you're making if you have a catalyst that may be doing a copolymerization of lactide and glycolide, and you wanted to try to tease out what kind of material you are making, and that's a good way to use that technology. So more recently, Jeremiah Johnson has been exploring a different way to control sequence that I think is pretty cool, and that is to use an exponential growth method. So it's still a kind of a protection, functionalization, coupling strategy. But what he decided to do was a little bit different. So he's using this kind of alkyne epoxide, which you can then treat with an azide and protect the alcohol to make this reagent here. If you have the enantiomer of this compound, right, that would be this kind of epoxy alkyne. Instead of doing the azide cleavage of the epoxide, if you deprotect the alkyne to then reveal a terminal alkyne, that sets the stage for a click reaction. And so these monomers you can then click together to make a dimer that now has an S enantiomer on the one from the one epoxide and the R derived from the other epoxide. And then you can go through another sequence where you do the azide opening. You could take some of this monomer and separate it and do the TBAF deprotection, then make the S and the R. And then if you do the click reaction again, now you have a tetramer. So before, with the peptide synthesizer, you're putting one on at a time. So you have linear growth, monomer, dimer, trimer, tetramer. But what's cool about this method is that you start with a monomer, you go to a dimer and a tetramer. And if you keep on doing that sequence, every round is exponential growth. So it goes monomer, dimer, tetramer, octamer, 16mer, 13mer, 32mer. So it's easier to get to higher molecular weight polymer. You don't have to go through as many cycles to get to high molecular weight polymer. Moreover, you can choose to then to make different sequences depending on what you decide to add in each step. And so you can have really good control over sequence. And so Jeremiah showed that you can make these really high molecular weight polymers, which would be very difficult to do using a peptide sequencer. And later on in this paper, if you're interested, I direct you to this Nature Chemistry paper. He shows how you can not only do this alternating AB stereo polymer, but also change the identity of the monomer. Okay, another thing that you can do is make a customized monomer. And so this is a really good example from Mark Hillmeyer's group, where they took these octadiene type molecules and using some standard organic chemistry, were able to convert them into these isomeric species that then can undergo ring opening metathesis polymerization. And so if you do ROMP on these polymers, you can see that you make two polymers that are regioisomeric with one another. And these are kind of mimics of what you would get if you did a ter polymerization between butadiene, styrene, and vinyl acetate. Moreover, if you hydrogenate those alkenes that you get from the ring opening metathesis polymerization, you then make polymers that would be something that looks similar from a ter polymerization with ethylene, styrene, and vinyl acetate. But now you have perfect sequence control because in the olefin metathesis reaction, this 3-substituted acetate prevents tail-to-tail dimerization. So you get perfect head-to-tail metathesis events because sterics avoid the tail-to-tail dimerization and the head-to-head dimerization in this ROMP. So this is a really cool way to control sequences. If a clever design of your monomer and also understanding of the polymerization process can then lead to these sequence-defined polymers. And as you can see, these have very different glass transition temperatures, which is either from the regioisomeric differences or the stereochemical differences between these two polymers. Okay, and so finally, the last thing I wanted to talk about was catalyst control to control sequence. And so we've had several webinars on topics where we're using catalysts to control polymer sequences. And in fact, Professor Burkhart was here last month to talk about some of his great chemistry, which I've replicated here. And you know, depending on your choice of catalyst, you can change the structure of the polymer. So if you use an earlier transition metal catalyst like these zirconosines and methylaluminoxane, you can make linear polyethylene with ethylene. If you use a later transition metal catalyst, you can actually start to incorporate branches into that polyethylene depending on the identity of the R. But relevant to this discussion is the chemistry that Professor Burkhart didn't talk about in his symposium, was that if you take CO, you can actually make a perfectly alternating copolymer between ethylene and CO using a similar palladium type catalyst. And what this capitalizes on is the relative propensity for ethylene to insert into this palladium acyl compared to subsequent insertions of possible insertions of an acyl into a palladium carbonyl, which is thermodynamically unfavorable. And then also the relative rates for after the insertion of the ethylene to make this palladium complex here, you could envision further incorporation of ethylene to make polyethylene. But it turns out that the kinetics for this reaction are such that CO would prefer to react to break up this chelate, which then ensures that you get alternating ethylene and CO rather than a pure ethylene, polyethylene. And so this is really cool. So it takes advantage of the kinetics for a reaction here. In other words, the relative rates for ethylene insertion versus CO insertion, which in principle you could change by altering the identity of the catalyst, although this is still a challenge. And it's something that our center is interested in. Okay, so this brings me to the last kind of topic that I wanted to touch on in the last maybe 5 minutes here, which is reactivity ratios. So the reactivity ratios is the inherent reactivity of monomers, which often dictates its sequence. And so you can actually think about this CO ethylene copolymerization leading to a perfectly alternating copolymer as a reflection of the propensity for CO to insert into the ethylene as opposed to ethylene inserting into ethylene. So in other words, we could have a polymer chain that has a monomer at its chain end, which we represent with this star. It can then encounter that same monomer, which would in this example would be ethylene followed by another ethylene. That would lead to polyethylene. Or if this is an ethyl, it could incorporate CO, which could be the second monomer. And that would go with a different rate constant, K12. And so then you would have a polymer that would have that as the chain end. So the metal acyl in the example on the previous slide. Of course, after the metal acyl is formed, you also have two kinetic scenarios. One in which you can insert the ethylene monomer, which would have a K21, or it could insert a consecutive CO insertion. So that would be K22. So the relative propensity for these two monomers to insert into one another is often represented with these reactivity ratios, which is a ratio of these two rate constants. So the homopolymerization divided by the propensity for it to copolymerize. So if this reactivity ratio here is close to 0, then the denominator is larger than the numerator, and you get an alternating sequence. So if R1 times R2, if they're both close to 0, right, then both after insertion of the first monomer and after insertion of the second monomer, you get an alternating copolymer. However, if K11 is much larger than K22, so if ethylene would prefer to insert over CO or CO into CO, then you would get a value that is very large. And if you multiplied R1 times R2, it would be a very large number. However, if it turns out it's completely random, right? Then when you multiply R1 times R2, you usually get a value of 1. So these reactivity ratios, which you can usually measure by looking at the relative incorporation of the monomer into the polymer at very low concentrations, can give you a sense for the sequence of a polymer when you don't have this precise sequence control like we have in the previous slides. And so you can see here in this nice chart that my graduate student Eric developed for us, that you can see that up here in this, we have examples of blocky copolymers or statistical copolymers. And then way down here are random copolymers. And there's examples of this, but there's a whole bunch of space here, which is completely unexplored. And it's very difficult to access those because oftentimes what dictates the reactivity ratios is the inherent reactivity of the monomers, right? So that poses a problem for things. And so here's an example of reactivity ratios and some issues. So this is a classic, these are products of reactivity ratios for different vinyl monomers that undergo radical polymerization. And so here, say you wanted to make a random copolymer of butadiene and acrylonitrile, right? So if you were to do that, the reactivity ratios would say you have no chance in doing that. You would make an alternating copolymer. So that means that you can't use radical polymerization to make an alternating copolymer of butadiene and acrylonitrile. So we don't know what the polymer properties are of those two monomers if you were to do a radical polymerization, right? So you can kind of look at a lot of these different examples and get similar kinds of conclusions, right? So vinylidene chloride and acrylonitrile, it's tough to get anything that's random, right? And as you can see from the beginning of this talk, we may want to get a random copolymer if we want good properties. So how do we overcome reactivity ratios? And this brings me to the last few slides, maybe 1 or 2 minutes. I know that I'm getting close to my time here, and I want to make sure there's time for discussion. And this is where switchable catalysis comes into play. And so our center is interested in temporal and spatial control of catalysts. And I think the way I think about switchable polymerization reactions as a way to overcome inherent bias for monomers in polymerization reactions. So here is an iron-based complex that my lab has developed for the switchable polymerization of lactide. In this case, when it's in the iron 2 oxidation state, it has 100% selectivity for lactide. When it's off in the iron 3 states, nothing is happening. But if you have an epoxide monomer, it's on. So it's the exact same catalyst. It's just the different oxidation state of the catalyst. And so the way I like to think, one way to think about these switchable polymerization reactions is that over here we have a reaction that's 100% selective. So reactivity ratio of like 1,000, right? When it's iron 2, but when it's iron 3, then it's 0, right? For this monomer. But in contrast, you get the reverse for these epoxides. So now you have changed flipped the script such that the reactivity ratio can be controlled by the catalyst, not by altering its structure, which is a good way to do those kinds of things, but instead by changing the mechanism for the polymerization reaction, right? And so this allows us to do cool things. So for example, if we have a mixture of those two monomers, we may think about making a polylactic acid, polyether, and polylactic acid block, which we can then control by adding oxidants and reductants. And of course, Paula has done this kind of thing as well as our group. And she was the first one to discover, her group was the first to discover this kind of redox switchable copolymerization reaction. And I love this example because these monomers are so similar to one another, caprolactone and lactide. And the catalyst is being switched on and off through this side chain, the backbone, the ferrocene backbone. And when she does the copolymerization, she can make these very interesting block copolymers that have predominantly polylactic acid when the catalyst is in the reduced state, and then kind of a random copolymer of polylactic acid, or I guess it's a gradient copolymer, excuse me, of polylactic acid and polycaprolactone, which is really cool. Our group later then showed that you can use that redox switchable polymerization to make pure block copolymers of polylactic acid and polyethers, which Paula's group has also shown with different catalysts. And so hopefully you can see how this kind of a different perspective on switchable polymerization, maybe from a polymer chemist perspective, to control polymer sequence and how we can alter polymer sequence. And so these kinds of things are, as you saw, except for some really early examples from the 1980s, most examples that I showed you today have come about in the last 15 to 20 years. And that's because we're still learning about all the different ways that we can control sequence in polymers and how it can be beneficial. So I really think that polymer sequence is something that will become very important, not only for dictating polymer properties in terms of mechanical properties and thermal properties, but also, as I showed with the nice examples from Tara Meyer's group, with controlling degradation rates as we think about degrading our polymers and using, in addition to using them for their properties. Okay, with that, I think we have about 10 minutes left, which is kind of perfect. So I'm happy to conclude at this stage, and I think it's an appropriate time for us to go to discussion. Thank you very much. How was that, Paula? Was that good?
I was telling, actually, I was with Christine and Henry, and I said, I'm not going to like insult them and say I'm disappointed that I'm with center members only. I was telling them I really enjoyed your tutorial because you talk a lot more polymer chemistry than I do, and then I actually think about. So I learned stuff, which you know, I hope everybody did. So
yeah, it's good for me. Yeah.
And I'm going to tell you, I answered that question with the elastomer. I answered correctly, but only because my mouse slipped, actually. I was going to answer it incorrectly, and then I clicked on the wrong answer.
Wait, you don't have to tell me that.
One of the few people who answered correctly. I wonder how many people answered incorrectly. Like.
All right, we should answer questions. It looks like mostly center folks, but I see Malcolm is here, and also
let's see, yeah,
Wang Yan, right?
But Actually, Christine had a good question for you.
Okay.
I think very appropriate. So.
What's up, Christine?
Great talk, Jeff. And I guess my question for you is, you presented a diverse array of very interesting strategies for sequence control. Is there one that you find or are thinking is the most promising? You can either think of it as where the field is right now or also in the goals of our center.
Yeah, I told you it's a good question.
Yeah. I think every single one of those methods has pros and cons, right? And so I think that it depends on what your application is. So one of the applications I didn't mention, which is a really cool application, is for identifying things. So like what Jeremiah is doing, it provides you kind of with a way to make kind of a barcode. And so you can envision having a molecular barcode that you can put on anything. And so people are interested in barcoding like currency, for example, to prevent counterfeiting. And so if that's the goal, then what you want is something that has a very precise capability to incorporate sequence. So the solid state peptide synthesizers and the methods that Jeremiah Johnson's working on and similar kinds of methods where sequence specificity is perfect, those kinds of applications are best. But those kinds, even though Jeremiah's system like has this, you know, escalating exponential growth, there's still like, it's not the best for changing the polymer to make different properties, right? You're stuck with this azide every repeat unit, and you have a hydrocarbon backbone, so it's not degradable. And so it's not very versatile for that. The strategy you might be able to apply to different monomers, of course, but so if you're interested in making engineering materials, I think some things like the Segmer ideas, if you could figure out how to make that catalytic, that would be really cool. Or our redox switchable polymerization reactions, I think have a lot of promise if we could figure out how to do them quickly, right? So right now, even with the ways that we're doing them, we can't, we're still diffusion limited. And so thinking about ways to switch fast is I think would be very cool and impactful. And I think that could also kind of change the game if you're thinking about engineering polymers. Does that answer your question?
Yeah, definitely. And for rapid switching, maybe more around the kind of like photo initiated or
light
something like that. Yeah.
I think light's the answer there for sure.
Awesome. Thank you.
You're welcome.
So Jeff, I have two questions.
Sure.
Can I? And the one is kind of technical, one is maybe kind of very weird. The first question is in the poll question. I still don't understand why the chirality changes how fast the polymer decomposes. In the question that you asked.
Why the stereoregularity
of
the polymer changes it?
Yeah.
So it turns out that the stereoregular polylactic acid is very crystalline, whereas the stereoirregular is not very crystalline. And so the amorphous polymer it adopts a structure in the solid state that makes it easier for water to access the ester. So it's a consequence of the crystal packing of the crystalline polymer domains, and the stereoregular polymer has more of those than the stereoirregular.
Yeah, but even the one that, I see. Okay.
John, when you think when we're talking stereoregularity for polymers, it's like you're talking actually different substances. It doesn't matter that the monomer is the same, kind of, because you have this repeat unit that ends up very huge, right? So we tend to think of enantiomers for like small molecules, but polymers, we forget they are huge. So basically you have a totally different structure.
Right, and if you think about it from that standpoint, think about this big molecule as just being a really small molecule. At every repeat unit there is a stereogenic center. Mm-hmm. And so if you change the stereochemistry of that stereogenic center, technically what you're making is a diastereomer. And so those diastereomers can have different properties. And so if you think about it in that way, if you have let's say you have a polymer that's 100,000 molecular weight and has a repeat unit that you can change the chirality at every repeat unit, that's a tremendous number of diastereomers, all of which could in principle have unique properties. And what's kind of neat is and amazing about catalytic science is that people have developed ways to make those polymers very stereo irregular, all kinds of different things. And so Lloyd talked a little bit about catalyst design, and that's something that I don't think that polymer chemists get enough credit for. Like a lot of organic chemists talk about asymmetric catalysis, and they forget that polypropylene's made isotactic 99.999%, and they're like, oh wait, I make 3 stereocenters in my molecule, and I'm like, big deal.
Yeah.
Call me when you have 1,000, and then you can talk about polypropylene with me, right? So they just go, oh, that's a big molecule, it doesn't count. I'm like, why not? Well, at what point? And then I said, when does it stop counting?
But
Okay.
I also
So-
want to illustrate with a joke. So I say that the only Nobel Prize that got that was awarded for changing a hydrogen with a methyl was for propylene polymerization. So Nata, so Ziegler-Nata and Ziegler-Nata, that's exactly what he did. He looked at Ziegler's chemistry. Ziegler did ethylene polymerization, and he realized the importance of propylene, basically stereopolymerization.
Right. You don't get any stereochemistry with polyethylene. That's right.
And yeah.
So the next question is kind of, I'm not sure, you may hate me now, because the food we eat is polymer, right? Because and I know some bread are much harder than the others. Is that really because of the sequence of the sugar in the chain, or it's not
What makes
related?
the bread harder? No, I don't think that's related to the.
So it's this mechanical property of the bread is nothing to do with the sequence of.
I don't know for sure, to be honest with you.
Actually, that's why I don't know.
Yeah.
Well, I think it gets way too complicated because it's about how many air bubbles you get into your polymer matrix, and
because when you talk about PCR peptide synthesizer,
also
remind me the starch have a food synthesizer, and that's the reason I ask about this.
Sure, but the bread has so many other things in it too, right? It's a composite material, and so it's very complicated.
Okay, yeah, I just got inspiration from the food synthesizer in Star Trek, right, and peptide too, right?
Yeah. Any other questions?
I think Henry said he's thinking of one. Is Henry still here? Maybe he's still thinking. Malcolm,
yeah, I'm here.
Do you want to ask a question?
Yeah, well, I was thinking about the redox switching that Jeff talked about at the end, and thinking about how are there methods for switching selectivity and polymerization from one monomer to a different monomer, let's say just 2 monomers for simplicity, that aren't catalyst centered, like conditions, or yeah, I guess I'm thinking mainly of conditions like solvents or additives that could change.
Sure, people have definitely done that. And I think one of the examples that comes to my mind is Charlotte Williams's work, where she adds CO2. And if you add CO2, you can kind of switch on a copolymerization with epoxides and switch off. So you can add CO2 and you have a switch where you add CO2 pressure and then you take CO2 away, and it changes kind of the reactivity. But yeah, certainly people have done those kinds of things. People have used pH to change the structure and the reactivity of different monomers. And that's another trigger that people have used to switch selectivities. People like Brett Forrest have developed ways to convert radical polymerizations to cationic polymerizations. And so using stimuli like light and electrochemistry actually to do that. And so certainly that has been done, and it's a good idea. I like those ideas. Reagent.
Thank you.
So Malcolm had a good question.
What's up, Malcolm? Good to see you.
Hey, Jeff. It's a great talk. How you been?
Good. I'm doing well.
Good, good. I miss the beard.
Oh, yeah, you're the only one.
I was going to say, yeah.
But I was talking to Lloyd, and I mentioned in the breakout rooms, and I mentioned I've been talking to Polly Arnold a lot in the last few months, and she recently has done some like rare earth catalysts for cyclic PLA synthesis.
Right.
And I noticed in a lot of these talks that you all have given, specifically the ones that are centered around the polymerization, the redox switchable polymerization catalyst, everything or most everything was linear. And so I was telling Laz, this probably like, maybe that's easier, like, because I know this is like the first, what is the first phase of the CIC. So I was like, maybe that like practically is like lower hanging fruit. So it might be easier to get stuff out quicker. But I was curious if anybody had considered like for a second phase or somewhere down the line, the usefulness of developing additional catalysts for cyclic polymerization as opposed to just like straight linear ones.
No, yeah, that's a great question. Certainly architecture and hierarchical structure is very important for polymer properties. And, you know, after talking to Polly, she probably was talking to you about the importance of the chain ends in polymer entanglement. So if you take those chain ends and you tie them together by making them a cycle, they don't entangle as well. And so that changes their polymer properties. And making cyclic polylactic acid, for example, Bob Weymouth has done as well at Stanford. It's challenging to do those kinds of things and to develop and to do that on purpose, right? And Poly's system's really nice.
The cerium one.
Yeah, that's a really cool way to do that. Bob Grubbs has a way to do that with ring opening metathesis polymerization that Chris Bolowski developed when he was a graduate student in Bob's group, and that's a really cool way. It just kind of backbites and it makes it cycle. It's just kind of neat to make cycles. But those are challenging polymers to make because you have this entropic problem. You have this really long polymer. How do you like figure out how to tie them together, right? And so all these methods that I mentioned have some kind of trick that keeps the two ends in close proximity to another so that they can close. We thought we had a cyclic polymerization for a while. And we were making cyclic polymers, but the problem is convincing yourself that you're making them and also that you're making them pure. You're not making them free of linear polymers. And so there's a lot of analytical work that needs to go into that to figure that out. And so that's part of the problem, but they certainly would have very interesting properties, in my opinion. I always thought cyclic polylactic acid would be a good plasticizer for linear polylactic acid, so it would make it more flexible. But no one's made it. I don't think the Weymouth group ever made enough of it, and maybe Poly has now, to try to see if it plasticizes linear polylactic acid and do the mechanical properties testing. So that the testing I showed you, it takes several grams of polymer in order to make the.
She mentioned it takes a lot. It takes the stuff that she does. It take because you know very well, you know my boss. I'm not a polymer chemist traditionally, so I'm used to working for with very small amounts of everything because it's like ridiculously expensive. And so Polly was telling me it's like very large. You need like a lot of this to do a lot of these studies.
Yeah, it's fun to talk to a polymer engineer, someone who doesn't make the polymers. They're like, oh, we don't need a lot of it, and they're like, cool. And then they come back to you and they're like, we only need about 100 grams of it. Like, all right, in my world, that's a lot.
Have that for you in a year.
Even a gram is a lot.
Yeah.
Can I jump in a little bit?
Sure,
I just want to say that cyclic, let's say polylactide is very cool, but none of the cases where they actually make cyclic polymers, it's not like they design them. So going back to like switchable catalysis, it's very difficult to figure out, at least in my mind, there's nothing that makes me think, oh, if I design, even on paper, if I design a catalyst for this is going, because I think a lot of it is a matter of, what is it, Jeff? Kinetic control, right? Like you have to actually get that backbiting as opposed to, the formation of the linear polymer.
That's right.
And I don't think we understand how that works. At least not enough even to make an educated or non-educated guess.
It's very complicated too, because it certainly is associated with how the polymer adopts in solution, right? If it wants to be a rigid rod, the two ends are never going to get together, and that's going to be dictated by the structure of the polymer, right, and the solvent and all those conditions, right? And so the stereoregularity of the polymer, all those kinds of things. So certain polymers, I think, are going to have a higher propensity to do it, and it seems like polylactic acid, there are a few examples of it. So I think it has kind of that propensity to do that, and also the methods that people have developed seem pretty creative to do that. But I think if you can come up with a creative way to make cyclic polymers that's general, that would be very interesting.
Yeah.
People would be
You gave us a lot of stuff to think about for our
For
phase
sure.
2 application.
For sure. Okay. Are we done? Any more questions? Malcolm, thanks for coming. I think you've been to all of them, right?
I've had to miss a couple because I've had like interviews and other stuff, but I try to make it to most of them.
Nice.
We thank you.
Yeah, thank you so much.
Well, I appreciate you guys, setting it up and everything. Are you guys, the last time I talked to Jeff, you said that, like I can email you with people that I would think, like, are you still doing like the guest lecture stuff?
Yeah.
We started them. Jeff,
I think Polly would really enjoy this.
It would be
Yeah,
awesome.
Yeah.
It'd be
of
great.
course, yeah.
Yeah.
I mean, Jeff is actually technically now in the guest lecture series.
Oh, okay. All right, so who do I email?
Because we had scheduling issues.
But next month, who's kind of forget who is our we have a guest speaker next
E.
month, right?
Do you know, or Hao Chan? You guys know. Is it Shelley Mintier? Do we know?
Let me check it.
We can check on the presentation. Yeah.
I think it's also, Malcolm, I think it's also on the website. If you go to the CIC website,
It is Shelley
Is
Mintier.
yeah.
Shelley Mintier
It's on the
on
list.
11th, May 11th.
I think the schedule is on the website too, so you can see who's coming up as well right after Shelley.
Oh yeah. I think we updated on the grand calendar.
Yeah.
No, I don't think it's on our website, Jeff. Actually.
Oh, it's not? We should put it up there.
We should. I was thinking. Yeah, we
Using
only.
the
I
grand
think we
calendar,
only put it after. So, but that's a good idea. We should announce the schedule in advance.
Yeah, I just get the announcements on Twitter. I follow like all of you.
Right.
So that's how.
That's good.
All right.
Okay,
that it?
anybody else? Okay, if not, thank you